Hey everyone, my name is Alexander Garganta. I work for Maracana, an IT training company focused on open source software. And as an instructor for Maracana, I've done a lot of training on Android, all the way from the internals to the SDK and app development. And in the course of my trainings, I've oftentimes encountered NDK, the Android Native Development Kit, which enables Android developers, you guys, to take advantage of code written in C or C++ and incorporate that code in your applications through the use of JNI, the Java Native Interface. I've actually always tried to stay as far away as possible from JNI, simply because I feel that it tends to introduce a lot of security/stability problems in the name of performance in my applications. But interestingly enough, it turns out that 25% of the Android applications on the market are written with some form of NDK or written using NDK with some form of JNI. So it is something that every Android developer should at least know about. So while this screencast is focused on Android developers wanting to learn more about NDK, it's also well suited for those that are simply here to examine what's possible in Android. Maybe they're building the actual underlying infrastructure of Android through building custom ROMs, but they just simply want to understand how the different layers fit together, and they want to understand how JNI works. I hope you enjoy the screencast.
So what exactly is the NDK? I'm actually going to navigate to the NDK page on d.android.com as I'm answering this question. So NDK, as I mentioned before, enables us to essentially take advantage of JNI, which in turn enables us to write code in C++ and then access it from our Java code base. Now, we know that generally Android applications are written in the Java language and they run on top of the Dalvik virtual machine. So we'll get to this in a moment, but we generally use NDK in the name of code reuse or increased performance. Now, NDK provides a set of tools, i.e. a tool chain, that enable us to compile our code written in C and C++ into the different target environments, so ABIs, the application binary interfaces, like the ARM v5, v7, or x86, which are the targets that our code base is eventually going to run on. It also provides a mechanism of embedding the native libraries. These are going to be the deliverables of the NDK. This is essentially what the compiled code is going to look like. It's going to ship as far as in form of native libraries. And NDK enables us to package these native libraries into our APK files, which is essentially what we'll finally deliver to our target audience to install on their devices. NDK also includes a number of system headers to essentially shared libraries that we can take advantage of and know that these headers are going to be and these libraries are going to be supported in the future. And finally, NDK provides documentation samples and tutorials, some of which we'll take a look at as we go through this screencast. So now that we know what NDK is, the next question is when or even if we want to use it. Why do I say this? Well, an average Java developer, when writing application code, is going to be generally more productive than an average C++ developer. Why? Well, simply because Java has a superior memory management model. It has a superior threading model, superior exception handling model, a superior set of libraries that it ships with, support for Unicode characters, and so on, that C++ tend to lack. So on average, we prefer to run or write code in the Java language, and which we know executes on the final devices, on the actual target devices, in the Dalvik virtual machine. Now, that said, why do we then talk about NDK? When does NDK make sense? As I mentioned before, there are two main reasons. One is when we have a lot of code that already exists or that needs to be written natively so that it can function on other devices, and we want to reuse it in the Java or on the Android side, we tend to write it in C++ and then wrap it using JNI and access it essentially from our Java applications. The second reason is performance. Google here mentions things like signal processing and physics simulation as examples of essentially sections of our code that are very sensitive to performance. But they also tend to be self-contained and very CPU intensive, and they don't tend to use a lot of memory. We'll talk about memory management specifically later. Now, do we want to write the entire applications natively, which we actually can? We typically don't for a couple of reasons. One is, as of Froyo, so API level 9, or I should say 8, Android ships with the just-in-time compiler, which is part of the Dalvik virtual machine. This compiler does a pretty decent job of identifying parts of our code base, that code base written in Java, that can benefit from essentially on-the-fly optimizations and caching, so that if that code base needs to execute very frequently, we can essentially compile it at runtime into native code, and then next time around execute it as native code. This is not something that's unique to Android or the Dalvik virtual machine. Of course, it's been around the block, if you will, even in the Java land for a very, very, very long time. But it certainly means that the performance advantages that the NDK once had over just unoptimized interpreted Java code that essentially runs as Dalvik code have somewhat faded. That said, the optimized Java code is still not going to be typically as fast as hand-tuned C++ written code, but it certainly isn't the only reason why you should consider increasing the complexity of your code base by going towards the NDK route. Now, the framework that Android provides is for us to write parts of our application natively and then wrap those parts and by a skeleton written in Java, or to essentially using something called native activity, implement an entire application simply in C++ with no Java whatsoever. If we go for the second approach, we are actually going to forego the use of certain features of the SDK, the Android SDK, like for example, services, content providers, broadcast receivers, and so on and so on. So if at all possible, we prefer to still maintain the overall code base of our application in Java and only write certain parts natively. Okay, so now that we know what and why we would use NDK, or I guess when, the next question is how do we get started? So again, on d.android.com, under the SDK tab, there's a section on the NDK right here. And so this actually offers links to download a version of the NDK. In this case, the actual latest version is 7B, or R7B as it's called, for the particular host platform that we'll be developing on. So I've already downloaded the one for my Mac operating system, so I'm just going to go and expand it. I'm going to go over here into my terminal, type tar jxvf, download, which is where it is, and then Android NDK, hit enter, and you'll see that it'll essentially uncompress the sources, the tool chains, sample code, documentation, a whole bunch of things into the Android NDK folder. I also like to create a symbolic link to this folder on my machine and then use or add the final pseudo directory into my path so that I can execute shell scripts from within the NDK directory, essentially from anywhere on my system. So here's what I'll do. I'll type ln-s Android NDK. Of course, on Windows environment, this is not something you would do, but what is useful is to be able to essentially add NDK to your path. In this case, what I have is somewhere in here, there should be NDK. NDK added to my path. I guess it's right here. Okay. If you haven't done so, you may want to consider doing that because it will come in handy later. But ultimately, we now have the NDK. You can see this is what we'll find in the directory. The main script, if you will, that we'll use is the ndk-build, although we'll talk about other sorts of tools later on. Okay, so now that we have the NDK installed on our file system, the next step is for us to actually build something with the NDK, and then through that, hopefully understand how to use it and what it has or doesn't have. So what I'm going to do is actually build an application in the Eclipse environment and then later on compile it from the command line. In order to build this, you will need the latest version of Eclipse, the latest version of the SDK, at least one platform, the latest version of the ADT, which is a tool set or plugin for Eclipse, already pre-configured and pre-set up. If you don't know how to do this, I suggest taking a look at d.android.com and then clicking on the SDK tab. Now, this is what we'll end up seeing. Let me actually, before we get started, switch over to my browser and switch over, actually, not to my browser, but this preview. Essentially, this is what we'll do. We'll create a Java library in which we will define some native methods. So those methods, as you will see, will implement later on inside of a C source file. Now, before we get there, what we'll do is, of course, we'll compile this library using Java-C, or Eclipse will compile it for us into the actual class itself. And then we'll use a tool called Java H-JNI to extract a header file from the original Java library, or better yet, the class file, which will then implement in our C++ source file. After we implement this, we'll actually create a makefile. There's two different parts to the make build system, the Android.mk and the application.mk. You'll see that only this one is required. We'll then run the NDK build. This is essentially the step where we'll do the NDK build, which is why we install the NDK. We'll produce the dynamic library. We'll then write a little bit of, some sort of a client app that will be, of course, compiled again by Eclipse into a class file. And then this application will use or attempt to use the Java library or the Java class, which in turn will load the native library and essentially provide the implementation that this application or this client application expects. Okay, that's our goal. Now, to get started, what I'm going to do is I'm going to go and create a new Android project. I'm going to give it some sort of a name, like for example, in this case, I'm just going to use Fibonacci as an example application. So I'm going to call this Fibonacci, say native, and I'm going to click on next, choose a build target. In this case, I have quite a few. I could choose any of the build targets. We're not going to do anything special, at least nothing that wouldn't work on, say, API level 8 or 9, but doesn't matter. In this case, I'm choosing the latest one. Clicking on next, and then I'm going to choose a package name. Like, for example, com.maracana.android.fibonacci native. Okay. And then I'm going to create an activity, for example, say Fibonacci activity. Minimum SDK 15. Again, I'm just using this as an example. Feel free to go and lower the SDK to something like 8 if you want to be able to try to run it or upload it to market, for example. So click on finish, and this builds a basic structure of my application. It's going to take a little bit of time for Eclipse to go and figure out that there is in fact the R file, and for this red section to go away. And now it's done. Okay, so the next step is for us to actually create the library itself. So we do this by right-clicking on this, the package, and creating a Java file, I should say a Java class, that I'm going to call, for example, fiblib, just some name that I chose to do, and clicking on finish. This will essentially create an simple class file. Now, this class file is just to show you this class file. It's basically this library right here. Now, you don't see this, but it's already been compiled by Eclipse into a native class. So we actually have all of this already done. Of course, we haven't defined anything there, so it's really useless at the moment. Okay, so let's go and define something. Okay, so what we'll do is define, for example, 4 different implementations of the Fibonacci essentially algorithm or sequence. 2 implementations are going to be written in Java, 2 are going to be written natively, and we're just going to use it to test performance. Later on, we'll introduce other things into the mix, but this is just going to be to get us started. So, for example, the naive Java implementation may look like this. Public, static, long, fib, JR. I'm going to say J is for Java, R is for recursive. So given some sort of an N, which is going to also be a long, I'm going to say, well, return if N is greater or less than 0, for example, return 0. Otherwise, if N is equal to 1, return 1. Otherwise, return fib of JR of N minus 1 plus fib of JR of N minus 2. So this is how essentially the Fibonacci sequence is defined. Nothing too special, nothing too exciting. Now that I have this, I'm also going to define a native version of this method. Public static, native static fib J, NR for native, long N. This is essentially J and I. What this means, I'm forgetting one part, which is the return value. I'm essentially saying here that the body of this method doesn't exist, it'll be provided natively. It's kind of like if you're creating an abstract method, this would have been an abstract class. You could say an abstract method, somebody else will implement it. Well, in this case, somebody else will be our native code, which we have to write. So then I'm going to define a version of the same Fibonacci algorithm, but this time around I'm going to use the iterative approach. So public, static, long, fib, ji, I for iterative, long n, and I'm going to say return, not quite. So for example, long previous equals, doesn't matter, -1, long result equals 1, and then for some sort of long I equals 0, I less than n, I plus plus, we are going to say give us a sum, so sum of result plus previous. Okay, so this actually matters, so that's why we initialize the previous and the result to -1 and 1, so that initially they're going to cancel out. And then previous equals result, and result equals to sum. And all we need to do is return the results. And now we have the iterative version of the Fibonacci algorithm. And finally, we're just going to go and say, for fun, public native, doesn't actually matter in which order you define them, but I like to do it this way, static, long, fib, ni, long, n. Done. So this is essentially our entire fiblib library. That's, if you take a look at this, this is what we've now built. So now this part is actually done. And to show you that we have even the library class, I'm going to go and open up my terminal. I'm going to go to the directory where this is located. So in this case is under, I should say, workspace, courseware, Android, out, workspace. Again, I know it's confusing. And there you'll see that I have my Fibonacci native project. And there you'll see I have the bin directory, or ls bin, classes, and then of course I can go and type com, boom, 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 and here is my class file. So that part is done. The next step is for me to build the or extract, I should say, the shared, let's take a look at this, the header file. Right now, I'm going to use a tool called java-h-jni to extract this. Later on, you'll see that you don't even need to do this step. There's another way of registering or binding native code to Java code without the need to worry about specific namespacing or the mapping rules. So for the time being, we'll actually do it this old-fashioned way. So What does that mean? First of all, I'm going to create a directory called JNI. Now, why am I creating this directory? Is because that's where NDK expects to find native code. Okay, it's by convention. And now that I have this, I'm going to run this tool called Java age-JNI, and I'm going to say I want to go and class path load classes from my bin/classes directory and output the header file into, so the destination is the JNI directory. And I'm specifically looking for a class by the following name, com.maracana.android.fibonacci-native.fiblib. Enter. If everything worked correctly, under the JNI folder, I should now have this header file. So what do I do then? Well, let's take a look at it. I'm going to go into, first of all, Eclipse and do a refresh of my project, because by doing that, I get the Eclipse to discover the new folder. And now you'll see that I have this file. Let's open up this file. Notice, by the way, this file looks kind of good, meaning it's syntax highlighted. And the reason why this works is because in my Eclipse, I actually have CDT, which is a set of plugins that enable me to write native code right in Eclipse. It's not just a Java editor, it's also a C++ editor. You can certainly go and add that support to Eclipse through help and then install new software, and then you can search for CDT. Now, let's take a look at this resulting file. Why this file, what does this file define? Well, fiblib, you'll notice, has a certain package name, and it has a class name with certain native functions, or I should say methods, but ultimately they'll become functions. So now check this out. In C, we don't have the concept of namespaces. So instead, in order for later on Java to be able to invoke these functions written in the C language, or I should say, I guess in the C language, we'll need to somehow map from the Java namespace into a flat namespace of C. And the way this is done, at least with JNI, is that this function, like for example, fibnr, is prefixed with a Java underscore the package name underscore the class name, and then finally the function name. Notice that function name takes in 3 arguments: a pointer to the environment, the point to the reference to the class within which it is to be found, and the JLong, which is essentially, as you will see, the n itself. This is the version of this function at least for this fibnr, and here's the same function for fibni. Okay. So now that we have this, the next step is for us to go and I'm going to actually copy these 2 functions like so, or I should say, it's probably easier to do it this way. I'm going to copy this entire header file like so, so copy, and then go over here and type paste. I'm actually making a copy of the entire header file. Doesn't seem like the most logical thing to do, but you'll see in a moment. So I now have a file by the same name, except that it's the .c. So just to show you what we're doing, we've now essentially done all of this. This is what we have. I'm now going and creating this file. Okay, that file, as you will see, will import from the header file, or I should say the include. So now that I have the C file, here it is, I'm going to go and have the C file include the header file. So com.maracana underscore android underscore fibonacci native underscore fiblib dot age. Okay, done. And now I'm going to get rid of this, get rid of this, get rid of this. So all I'm left with are the same function signatures or prototypes that I've done before, except that now I'm actually going to provide the bodies of these 2 functions. So here is, our first function, the fibnr, that takes in a pointer to the environment, a reference to the class, and then the n. Now, the pointer to the environment is going to come in handy later. You will see exactly how. The class is given to us so that we can reference this fiblib class. Had this been a non-static method, then we would not have been given a reference to a class, we'd be given a reference to the object. So this would have been called the J object, or it would have been of type J object. And finally, this is the n itself. So just to show you back here, remember how this fib nr takes an n? Well, here we get that n. Now, why is this n J long? Okay, well, the thing about JNI, as you will see, is that JNI is generally meant to mostly not implement a lot of logic, but rather map Java data types onto C data types so that we can invoke code that is written just natively without any regard to Java or the JNI. So essentially what that means is that we have to map from one data type space into another. In Java and Dalvik, as a result, the data types are fixed. We know exactly what they are regardless of the underlying infrastructure or architecture. So we know that Boolean is essentially unsigned, happens to be unsigned 8 bits. A byte is always signed 8 bits. That char is unsigned 16 bits. Short is always 16 bits. Int is always 32 bits. Long is always 64 bits. Unfortunately, in C or C++, something like, for example, long will depend on the our underlying architecture. So if you're on a 64-bit platform, long is going to be 64 bits. If you're on a 32-bit platform, long is going to be 32 bits. In Java, that doesn't work that way. It's always 64 bits. So because of that, we can't really use C types without worrying that we may actually, for example, overflow our values or truncate our values. So basically, instead, we're going to use JLong. So we know exactly what the type this is. And this is really nothing more than a little type def. Where does this come from? Well, notice how here we're including this header file. Well, that header file is in turn including the jni.h. jni.h, as you will see, defines a number of things, including this JNI environment, the J class, as well as all these other data types that we now see. So let's go down here. I'm going to do the same thing that I've done, name these parameters here. I'm going to do the same thing over here. And so now it's just a matter of me implementing the code. So for example, for this version, I could just be lazy and copy the Java version. So I'm just going to, boom, copy this code. In fact, copy all of this. Go to the C implementation and literally paste it. The only difference is that now this becomes a JLong. This becomes a JLong. This over here becomes a JLong I. So I can't, this is not quite C99, so I can't declare this inside of the for loop statement. This becomes a JLong. Okay. This becomes a, basically, same as before. Nothing too exciting. Move this over here. In fact, let's use same kind of indentation as I did do in Java, so it's consistent. And now I just provide the result. Okay, done. So again, this is just the same code but written in C. For the other one, which is this function, well, the problem is I don't want, because this is recursive, and recursion is involving, if you will, because you're copying stack variables. What I'm going to do, I'm going to create a helper function. This is going to be a little static, which means internal JLong, say fib, just fib, that takes a JLong of n, and simply goes and returns the Fibonacci like this and this. So this essentially is equivalent to what I have in Java. The only difference is that I'm now going to call into that function from here and say return fib of n. So essentially, the reason why I did it this way as opposed to making this into a recursive function is because I don't want to copy these two arguments every time I recurse into my own function. But I should now be essentially done. Appearing, of course, any sort of typos or mistakes. This is where we are now. We've written all of this. Okay. The next step, of course, is to build the makefile, and once we have the makefile, we can produce our final result. So let's get that done. Okay, so I'm gonna go back in here and create a new file. I'm gonna call it, it's just a file, I'm gonna call it android.mk. That's it, it's here. And what I'm gonna do is in this file, I'm going to create a number of entries. We'll actually talk more about this file. I just want to get it working first, and then we'll come back to what exactly, do all these things mean and what else can we do here. So first of all, I'm going to say local path is, and I'm going to call into simply a GNU macro called call my dir, which sets up the local path variable to the current directory. Then I'm going to say include, and I'm going to say clear vars. What that means is that it'll clear all of the variables that start with local except for the local path, if any exist. This will become more interesting later. Then I'm going to say local source files. I only really have one, and this one file is the Maracana Android Fibonacci native _fib lib. And .c, that's the source file. And finally, I have to define a local module. What is the name of the final shared library going to be? Well, I just for consistency reasons, I'm going to call it exactly this, of course, minus the extension. Now, this just defines the necessary arguments into the final part, and that is include build shared library. What that does is essentially executes, think of it as a function that says, what do I need to build and where do I need to store it? So it builds this code as a shared library by this name. We'll see the final name and what it actually is set to. Now what we're going to do is actually execute a build to test it out, and then we'll move on to a few more things to build, like, for example, the UI. So let's try it out. NDK-build. If I hit enter, everything works correctly. It compiled by default an ARM-based shared library that I should now be able to load into my application and start using it. So now that we see that the compiled library goes into the libs directory, in fact, we can take a look at it like this: libs arm lib Maracana SO. You'll actually see that's where the final product is. And if I do a file on this file, which is a Unix or Mac command, you'll see that this has been compiled as a 32-bit ELF shared library object specifically for ARM. Now, let's see how we basically can change this, or how we can expand on this. So what if, for example, we know that we're going to run our application or applications on non-ARM environments, or ARM environments with, say, the v7 instruction set support. So how do we essentially control the application binary interface, or the ABI? Well, there's a couple of ways. One is we could simply go and rerun the NDK build command. Like, for example, I can type NDK build clean to get rid of all the the files. And now what I can do is I can say, hey, I want to actually run the NDK build, but I want the application ABI to be, for example, x86. Hit enter, and now it's going to compile specifically for x86 as opposed to the ARM ABI. So I can show you file libs x86, the file, and you'll see that it's for Intel 386 instruction set. So what if I wanted all of them? Like, another approach would have been for me to say all, hit enter, and what now I would do is it would actually build or compile this for all the ABIs that it currently supports. So right now you'll see that it has ARM ABI, ARM v7 ABI, and the x86. You can also control not say all, but say only the specific ones. For example, let's say that you specifically need the use of the neon instruction set available in RMV7. So then what you could do is you can say, I want this one. So you copy this and you paste it. And I want x86, for example, maybe because you're using the equivalent to SIMD instructions in x86. You just need to basically pass this as essentially a setting. You hit enter, and now it compiles it specifically just for these two environments. Now, specifying the ARM or the app ABI on the command line is all nice and dandy, but what if we actually want this to be fixed as part of our project? So as opposed to saying it like this, we kind of want to go and configure it in a file so that anyone, whoever goes and runs the NDK build in our projects directory, compiles the ABIs that we instructed them to. So now what we're going to see is another file that we can optionally create. In this case, you'll see it's called application.mk. It is similar to Android.mk, but the difference being is that Android.mk is specific to how to compile the code, whereas application.mk sets up some global properties or environment variables, one of which is the app ABI. So let's go and create that file. So what I'm going to do is I'm going to go over here into my JNI directory and create a new file. So a new file, and say application.mk, hit finish, and here's a file. All I now need to do is go back over here where I, for example, specified the app ABI. And now what I can do is I can copy this and go, for example, into my application MK and say, oh, by the way, I want to, for example, include all of the supported ABIs. So now that I've done this, I can do an NDK clean so that I'm back to square one. Oops, NDK build clean. I'm back to square one. I'm going to clear the screen and type NDK build without actually specifying any additional parameters on the command line. Hit enter, and as you see, it actually goes and compiles the same code 3 times for 3 different ABIs, the ARMv5, v7, and x86, effectively making our application a fat binary. So you'll see under the libs directory, in fact, I can just do like this, find libs. You'll see there are 3 different subdirectories, each one containing the same essentially library, of course compiled for the different instruction set. Now, hopefully that explains the ABI, but one thing I haven't quite explained is how does this work at runtime? How do we actually load this library? How do we load the correct library? Well, one thing we'll see is that once our application gets packaged, all of these libraries that we see here, all the different compile libraries will become part of our APK. But at the installation time, so once our application is actually installed on the target device, the system, because it inherently knows what is its optimal ABI, it will pick one of these libraries and install it as our application library going forward. So now, how do we actually tell the system to load the library so that we actually can take advantage of it, so we can bind our Java functions to the library's functions? So that's the one step that we missed. Notice that this library is called, in this case where it gets loaded, it's called lib com Maracana Android Fibonacci native fiblib.so. That happens to be the full name. So, and in fact, where this name is defined is inside of this Android.mk that we took a look at previously. So right here, what I have highlighted. So this is the essentially logical name of our library. The fact that it happens to live in a particular directory and the fact that it has prefixes lib and excuse me, and the .so is just a side effect of how essentially JNI, in this case NDK, work. So what I'm really interested in is this name. This is the name in the middle. That's the name that I assigned to my library. So what I'm going to do is I'm going to go back to my Java class, which this is where I implemented the 2 Java methods and defined the 2 native methods. And I'm going to go over here and say, hey, when this class is loaded, okay, and the way you can do this is you can create a static block. You can say when this class is loaded, I want the system to help load a library by a particular name. The name is essentially the name that I gave to this class at runtime, or so I should say, the name that I gave to this class in the Android.mk file. So at runtime, when this gets executed, the system will automatically prefix this with lib and add the suffix of .so, and then search for the library in a well-known directory. That's essentially what NDK will enable for us. And so now we're essentially done. We have created a library, and we've compiled it. So to kind of take a look at our diagram, we have done all of this. All of this is now complete. The only remaining part is to actually use our library, and then through that, use the Java class, which will then use the dynamic library and see that everything works. So let's actually try that out. Okay, so we start off by looking at our client now, the Fibonacci activity, which is going to eventually end up using the fiblib, but we want to make it slightly more interesting. For example, we want to make the UI allow us to select the algorithm, specify the n that we want to get Fibonacci of, and then click some button to, for example, get the result. So we'll, I guess, start off by looking at our layout, which is right here, and here is our main.xml, and here's the strings.xml, which defines its values. Like, for example, here's the hello world little string, which will, for example, change into, I don't know, get your Fibonacci numbers here. And so, I don't know, maybe we'll capitalize this. And so now that I've changed the string, if I go to the main.xml, you'll see that's what that shows up. And if I want to make it slightly nicer, I can say, okay, I'm going to change its gravity to be centered. So gravity center. Okay, so now it's centered, and maybe, I don't know, I can also change the text size, and we'll just hard code it here, something like, I don't know, 25 SPs. And so now we have the initial title. So next, what we want to do is add some sort of an edit button, form widgets that the user will be able to type in their number into. Now, of course, I always keep forgetting where the edit buttons are, so for some reason they're not under the form widgets. I was going to assume that they're going to be under here. So I just want to find, for example, this one. The reason why I chose that one is because I like number 4 too. No, I just want something that only takes in numbers. So you'll see that basically what happened is that this became an edit text that has the input type of number. I can assign this some sort of an ID. This will be necessary later on, so I can actually know what the n was. So I don't know, maybe I'm going to call it input. That's it. I don't have to get much fancier than that. That's the where the user is going to type in the number. The next one is going to be some sort of maybe a radio group. I want the user to be able to select from different options. So I'm actually going to go back to over here, form widgets, and here is a radio button. But of course, I want to somehow wrap these inside of a radio group, which I can never really quite find. I'm not sure where they keep them. Anyway, so I guess I'll just wrap it up myself. So here, I'll actually just drop to the XML. You'll see that I have a radio button that, for example, the text for the radio button could say something like, this is going to be the strings of fib JR. That's the first one that we have here as an option, which of course doesn't exist. And this is going to be the radio. We're going to call this, for example, fib JR, so that we know later on what the user has actually selected. Or maybe just for fun, because we're going to use lowercase, let's call this type fib JR. Okay, so I'm going to click on save. This is going to complain. I'm going to go and say, okay, fix it by going and saying quick fix or command 1. Extract the style. I don't know why it's picking the style. That's a little odd. It's supposed to say extract text. Oh well. So I guess I'm going to go over here and in my strings and duplicate one of these. So on my Mac I can do command shift or command option down to duplicate this line and say this is going to be, fibjr. You might as well go and define the other ones. These are going to be the different titles the user is going to be able to select. So this is the JI, the NR, NR, and NI. So just to change these as well, NI, NR, whoops. I guess I should really look at what I'm typing, and NI. Done. So now that I've defined these, I can go back here, just click on save. This should, whoops, no wonder this didn't work. It's supposed to be a string, not a strings. Okay, so now what I'll do is I'll actually wrap all of these inside of, when I say all of these, I don't have the other ones yet, radio group. And so inside of the radio group, I'm going to have a lot of these radio buttons. So now I want to be able to select or know what was the selection, which radio button was selected. So the way I'm going to do this, I'm going to basically assign this sort of radio groups in sort of an ID. So for example, ID equals, maybe I'll call it, type. Of course, you need to go and have it be created. So plus ID. And I'm going to change the default orientation because I believe by default it goes vertically. So I'm going to change the orientation to be horizontal. That I think should get the job done. And so otherwise, I guess the layout width-wise, I'm going to have it match the parent. So width or layout width is match parent. I'm using control space just for auto completion, and layout height is wrap content, right? So only use as much space as necessary. On this radio button itself, I gave it this button an ID. I gave it some height. I actually want the height to be, I guess, match parent when the width would make sense. And on the height, so let's go and say match parent, and then on the height, I can probably leave it as wrap content. Of course, because these are going to be greedy, I need to also add the Android layout weight. So weight of something like, let's say 1, so that they're all exactly the same. I believe this should be it. So now what I need to do is just duplicate this 4 times or 3 more times. So I now have 4 radio buttons. This one is going to be the fibjr. We'll make this be a fibji. This could be, of course, this is going to say ji as well, which is the one we created previously. This is going to say nr. This is going to say NR again. And finally, we'll have a version that is NI for native iterative and NI over here. So that's it. This is where we are at the moment. So we basically have the title, we have the number the user is going to type, and then we have the 4 different radio buttons. That's what we've accomplished. We only need 2 more things. I want to have a button the user is going to be able to click on. So let's say a button that goes right here, and this button is going to have maybe, I don't know, we can call it, say, ID of button, for lack of a better term. Width, we can have it take up, match parent. Whoops, I don't know what I pressed. So let's go back. Let's go back here. So match parent. Width is the same, and then the text, I just don't like to hard code these things, so I'm going to say string / I don't know, button, for the lack of, again, better, or actually I should say output, because the other one was, no, let's just call it button. The next one is going to be output. Okay, so this doesn't work. So let's see if this allows me to create a string resource. It does. I'm just going to call it get Fibonacci result or something like that. And so now that we have that, let's see what this looks like. That's pretty good. Finally, we need some sort of a text area where we'll be able to drop the final result into. So here's a text view. Maybe we'll call this the output. That's where we're going to write the result into. So output, and we're going to have the width and the height basically be both match parents, so take up the rest of the space. And there's not going to be any sort of text. We should probably just get rid of the text. That said, let's actually just see where it's going to look like. It's going to sit right here. I do want to maybe center this. So, for example, Android gravity. Android gravity. We could say center, like that. And that should probably be it. I guess one more last thing is we can go and give it some sort of text size to make it look a little bigger, just so that it's easier to see. So something like, I don't know, 20 SP would be probably good enough. And now we really don't need any sort of text. This is going to be the output of our program. So here we are. I believe we have the entire UI designed. So this is the input, this is the selection of the algorithm, here's the button, and here's the output. Now the next step is for us to go and actually implement the Fibonacci activity. Okay, so let's go and do this. The first step is for us to connect to our UI, right? So we're going to go and define some sort of maybe an input, so private edit text input. That's where we're going to get our end from. Private radio group. That's going to be our type, and private text view. This is going to be our output. So those are the UI elements that we're going to be interested in over here. So now that we've here initialized the UI, we can say, okay, this dot input is going to essentially come from. We need to go and cast this. It'll come from. Whoops. What's going on? For some reason, the end button doesn't work as expected. Super dot find view by ID, and so ID is going to be r.id.input. So we've got that. We can do the same thing for the output. So, well, more or less the same thing. This is going to be a output. This is, of course, we have to cast it into the text view, and in between we'll have this dot type equals radio group super dot find view by ID r.id dot type, and I now think we have the three that we care about. And of course the last one is the button. We want to know when the button is actually clicked, so we can say button equals button super dot find view by ID. There's other ways of doing this, of course, but this is just simple enough to hopefully make sense. The real objective here is not to focus on the UI, but really on the JNI part. So now that we have the button, we can go and say button. So let's go and import this. So Command-Shift-O does the import, or if you're on a Windows or a Linux machine, it'll be a Control-Shift-O, organize imports. And so now button.set on-click listener. This we can make ourselves be the on-click listener. Of course, because we are not yet an on-click listener, this is red. So we can then have Eclipse help us by allowing us to be an on-click listener. So how I got here, I click on the red button, and now I can select this. Double-clicking on it adds the on-click listener as well as the appropriate import statement here. And now this complains because we're not really still an on-click listener, so we click on this and say add the unimplemented methods. There's only one method, which is essentially the on-click. Here's the view that was clicked on. Now, what we do in the view is we actually now need to do what the user asked us to do, which is to find the n. We then need to go and parse the string into a real n, and then go and do the calculation. So how do we do this? First of all, I'm going to say string s equals this dot input dot get text dot toString. Okay, so we now have something that's supposed to be an n, and we can go and parse it, or we can actually test for, well, if s is empty, and actually Android already has something called text utils. If you do control space, it'll do an automatic import, is empty s. So if this is already empty, which also includes null, then we can just go and say return. There's nothing for us to do. Okay, otherwise we can go and parse n. So we can go and actually assume, we should be checking errors, but let's keep it simple. So I'm going to say long n equals long dot parse long of s. And so we now essentially have the n. Now that we have the n, what we want to do is start a calculation. Now, let's do this the simple way, which is essentially we're going to go and check for what is the type, and then we're going to, based on the type, call the appropriate algorithm and then update our UI. So let's see. I'm going to go and say switch this dot type dot get checked radio button ID. I'm interested in which radio button was actually checked. Now I want to go and say, well, case r.id dot, for example, JR. So I know that's what the user clicked on. I'm gonna, figure out what I should do. So presumably this is where I actually invoke the appropriate algorithm. So how do I do this? Well, here's what I'll do. I'll initialize the result. So long result equals to, I don't know, nothing, 0. And then I'm going to say result. So result equals fib lib dot jr of n. That's the easy one. That's actually not in any way, shape, or form NDK specific, because this is all pure Java. And I'm going to just duplicate this case 4 times. So this is going to be a JI, for example. Whoops. JI. This could be a JI. This over here could be an NR. And this is going to be an NR. And then finally, this one is going to be NI. And this is NI. So we now have a way of initializing the result based on what the selection the user typed in. And so now that we're done with this, I guess one more thing I'll do just for fun is I'll also measure the time that it takes to do this. So I can say, for example, long t equals system dot current time millis. Or you can actually go and use the time. This is using the wall time. There's also, getting time for the, from the initial boot up of the system, which is probably slightly better, but this is what most Java developers do anyways. T equals system dot current time millis minus t. And so now we know how long this operation took. And so now what we can do is we can actually go and create a string, for example, something that will update the UI. So we can say, this dot output dot set text, and now the text could be some sort of a string, for example, fib. Let's actually format it. String dot format fib of some sort of %d, which is going to be the n, equals %d the result in %d milliseconds. So we just need to fill in the %d's, so the n, result, time, and we now are pretty much done. Now let's go and check this out, save this. The next step is to try to run this. that said, before I actually go and execute this, some of you may be thinking, well, hey, recursive, Fibonacci is not that fast. In fact, if n was something like, 20, 30, this can easily cause an ANR, whether here or here. ANR stands for application unresponsive and is a result of essentially us locking up the UI thread. Don't forget, all of this happens on the UI thread because this is all firing from the onClick event handler. So instead of doing it this way, which will work, but it's not necessarily optimal, it's probably better for us to do this in some sort of a async task. Now, so what I'll do is I'll actually refactor this code somewhat. I should have done this right from the get-go. But just to be, just to make it kind of nice and easy, I'm going to go and do it now. So here's a couple of things I'll do. First of all, I'll make the n be final, and you'll see in a moment why. Then what I'll do is I'll create a new async task, control space, async task. And I'm gonna go and say that the input to the async task is just void. We're just gonna pass everything through these copies of the stack. There's no progress, and the result is just gonna be a string, for example. So we're creating a new async task, and then in this async task there's gonna be, and we're gonna finally execute it at the end, which is gonna come in later. And in this async task we're going to have two things: as the code, the method that executes in the background, which is the one that takes a long time, and the method that runs in the foreground on the UI thread, handling the final result. So the method that happens in the background is called doInBackground. So we can actually have Eclipse fill in the blanks for us. So here's that method, and then there's going to be another method, which I'm going to go to source, override implement methods, which is going to call onPostExecute. That will actually fire when our code in the doInBackground is finally done executing, and then is able to transfer this output string into the input so that this executes on the correct thread. So let's go and move some code around. I'm going to take this code, which is essentially the code that takes a long time. I'm going to cut it, and I'm going to go and move it inside of this doInBackground. Okay. It's of course complaining that I don't have the type, so it doesn't really, where's the type gonna come from. Just to make it slightly, let's actually make it slightly simpler. I'm just gonna go and change this to say Fibonacci activity dot this dot type. Of course, I have to learn how to type myself. Fibonacci activity dot this dot type. So this is the reason why I'm doing this, is so that I can reference to this type variable that exists over here in another class. I can make this more optimal by making type not be private and so on, but that's not really the objective here. So that's this part, but this method is supposed to return some sort of a string, and yet I'm not returning anything. So what I'll do is I'll take this string, which we would have normally done or returned, and I'm going to take that string and go and return it right here. So return this. Done. So now what I need is to take that string that's going to come from here, from the doInBackground, and update the UI in postExecute, which is running on the correct thread, or will run on the correct thread, which is where it's safe to update the UI. So again, I no longer am going to, just like I did here to reference this type, I went and said Fibonacci activity.this. Here I'm going to say Fibonacci activity.this dot output dot set text, and I'm just going to say result. So now I'm essentially done. The only thing that's somewhat kind of missing is it'd be nice for me to maybe create some sort of a dialogue that will tell the user that, hey, their calculation is taking place. So how do I do this? Well, for example, I can go right here and say something like final, say progress dialog equals, and then I can actually go and say progress dialog dot show, context is this, the title is, I can just make the title be nothing, And then the message is maybe, I don't know, some sort of a, we have to figure out some sort of a message. And then I'm going to say true, true, and then dot, and then close it. Now I need to just define the message. Just in the interest of time, I'm going to hard code it and say calculating like this. Why do I have trouble typing? So go like this, and now that I have this dialog that will show up, I can go and down below dismiss this dialog now that everything's done, dot dismiss. And so now I have some sort of a hopefully nice and easy to work dialog. So if I did everything correctly, we should now be able to execute it. But just to show you what the final result looks like, we basically have an activity that implements the on-click listener. We have the three references to three of our UI elements or views. We then connect to our views. We prime the button to let us know when it gets clicked. We then have an on-click handler which extracts the n or the input, it parses it into a correct, hopefully into and doesn't fail into a long, and then goes over here in the onDo in an async task, executes the do in background, which goes and based on the type that the user selected, figures out essentially which of the Fibonacci library algorithms to run, and then figures out the time it took to do this, formats everything, and goes and sends us back the result, so that we can go and update the UI with the result. I agree that this is not the best way to write async tasks. For example, you should not create them as anonymous inherent classes, and you should support reattaching them to the activity in case, for example, activity rotates and gets recreated, or device rotates and gets recreated. And of course, this is also not the most optimal way to create dialogues. We should be using onCreate dialogue and so on and so on. But this is really just to kind of get some sort of a client application built so we can test our Fibonacci JNI code. Just to show you what we've done so far is we've basically just built this part. We now just have to package it all together, and then at runtime we'll have this, and hope if everything works correctly, it should execute appropriately. Let's try this out. Okay, so the way we're going to do this is we're going to create if you don't already have one, a new AVD. So I'm going to go over here and say I want to create a new AVD. I'm going to call it, for example, Android 15 NDK specific. I'm going to target API level 15. I'm going to go and say, I don't know, SD card 16 megabytes, and I'm going to change the resolution to be, I don't know, half VGA. So that's it. That's my AVD. I'm gonna now create it, and I'm gonna go and start it up. So start, launch, and it'll take a little bit of time. And once it launches, I'm actually gonna run my application as an Android application and observe what happens inside of the over here. We're gonna type adb logcat. Of course, we have to make sure that this connects. It's going to take a little bit of time. Sometimes it takes longer than I would like, but we'll just have to restart this. There we go. Okay, so our device is now booting. It's not yet ready to accept our application, but it will in a moment. And then when it does, we'll be able to take a look at how it deploys our application, and then of course how application actually runs or executes. So let's give it a little bit of time, and then we'll go back over here to Eclipse and test things out. Okay, so now I can close this, go back over here, and I should just double check this started. It did. I need to go and relaunch this. Sometimes it exits. So we're in business. And so now what I'm going to do is come back and right click on this, say run as Android application. Now, if everything's done correctly, I see my libraries are here, all my files compile. This should sometimes today go and launch it. So it did. It says displaying activity. So I'm going to go back here, unlock the device. Here it is. It doesn't say much about anything with respect to JNI just yet. But I do want to show you something before we go into actually running it. If I type ADB shell and I actually go into the com.maracana.android.fibonacci native, you'll notice that there's a directory here called lib. And if I go into that directory, ls-l, you'll notice that there is a library that happens to be ours. Now, the question is, which one is it? So which of these is we built, essentially, we compiled 3 different versions. There's one here, one here, one here. So it just so happens to be this one because this particular emulator is running on ARM v7. I can test this out. I mean, I can go and say, for example, just look at the size and just comparing the size of that to the size of these other ones. So I can actually go and exit this and do an ls-l of lib Fibonacci ARM -v7. You'll see that size and this size are exactly the same. Another thing I could have done is I could have said ADB pull this file, so just to download it, so I can actually see which one is being used. So I'm going to copy paste that path in this. Okay, I'm going to download it here into my current directory. So, whoops, oh, I have missing an extra slash here. Or extra libs, or lib, I should say. Okay, so now I have that file here temporarily, file lib Fibonacci or libcom. This is the file that I got, and it should say that it's, well, it just says ARM. For some reason I thought it would say ARM v7. So, oh well, at least we know it's ARM, and it should work. So anyway, I'm going to go and delete it. Because I don't need it here. And now I want to actually see what happens if I type ADB logcat again and clear the screen, wait for me to actually execute something. So for example, I can say right off the bat, give me a Fibonacci using native recursive 415, click on this, and it gives me that it's 610 in 3 milliseconds. And what's interesting is right now I can see as soon as I run this code, because my code tries to use fiblib, and fiblib has a static initializer, just to remind you, it's right here, that we added, and the static initializer says, I want to load this library. Because of this one line, Dalvik virtual machine goes and says, okay, let's go and find the library. It finds it in this folder. This is the path of this is what kind of predefined. It goes and loads it. It doesn't find any sort of onload function, which we'll talk about in a moment, but now is able to actually bind to it, and as a result, is able to give us the correct result. Let's compare this to the Java version. Does this produce the same result? If I do the NI, same result. If I do fib, is it the same result? This one is not the same result as this. So somehow I must have changed or implemented incorrectly. I guess I'm going to have to go and fix it. Okay, so let's take a look at our code. We have it over here. I realized that actually one thing I forgot to do is to make sure that this I goes all the way up to n, including n, not to 1 less than n. So that's my mistake, missing this 1 equal sign. So I'm going to have to fix the same thing in the C version. I probably made the same mistake because I copy-pasted the code, and I did. So say equals here as well. Now here's an opportunity for us to go and redeploy it. So I'm going to go over here and type NDK build. So to recompile it, so click on OK, that repackages it, and then I'm gonna go, I usually like to go and do refresh to make sure that Eclipse is aware of all the changes to all the files, because especially when I modify files from outside of Eclipse. And now I can go and rerun the same code. So let's see, go back, click on OK here. It should redeploy. And so let's try this again. 15 for JR. Same thing over here. Oh, now we get the correct result. Okay, perfect. Now, of course, if you try larger values like, say 25, this one will be extremely fast. It does it in, essentially 0 milliseconds. This one takes 14. This one takes 0, but this one may take slightly more. More than half a second. So, and it goes, very, very exponentially. Essentially, it gets more expensive as you increase this number. So don't use, anything above, say, 35, especially if you're using the recursive versions. Well, for the 30 ones, doesn't really matter how high the number is. So anyway, we now have a working version of our code base. We are able to invoke from Java the native functions. Let's just kind of see this. This is essentially where I'm invoking it. Now, what's nice about this is the client code has no idea that it's actually talking to the C code underneath the hood, nor does it care. All of that is essentially been abstracted by this function that just happens to be marked native, and then the binding from this native function to the C implementation happens as a result of the correct naming of our functions and methods. So now that we know this, I wanted us to take a look at one more little feature, actually two more features, but we'll start with one, and that has to do with logging. How do we know that this is actually working correctly? So let's do a little bit of logging. So logging from Java is pretty simple. We usually go and define some sort of a tag here, for example, private static final string tag equals, say, fib lib, and that's it. So now that we have that tag, we can go in here, say inside of this function, say something like log.d tag, fib ji of, and then we could paste in this n and close this. Okay. Yes, string concatenation is not the best thing to do, but it gets the job done. Of course, we need to import the log from the Android util folder or a package. We click on that and it gets imported. For this one, I kind of don't want to go and just copy paste this in here. I could go in here like so and invoke this. The problem is, of course, I would rename it. The problem is because this is recursive, this would be extremely expensive. I would see a lot of these log statements. So instead of doing it this way, what I'll do is I'll actually create a helper function like we did for C, call it private static long fib, long n, and this is where we're going to essentially do this code is going to just be part of this function, and this is going to be a fib and fib. Okay, so this is the recursive one, and then here we're just going to go and call that function instead. So return fib of n. Done. Now don't let this confuse you that we have a static fib function here and we have a static fib function here. These two cannot see each other, and the fact that they look like they have the same name makes no difference. In fact, this function, because it's static, is never exported, so it's not seen by anything outside of this native library. And this is private, so it's not also going to be seen by anyone outside of this particular class. So anyway, we now have logging here, and that hopefully will work. But what about logging from native code? Like, what if we wanted to do logging here and here? How do we do this? And by logging, of course, I'm referring to the Android's log buffer that everyone logs to. So essentially, I want our log cat to return, some sort of, or print some sort of entries that are coming from C code. So how do we do this? Well, it just so happens that Android provides a library to do exactly that. The only thing is we need to go include this library, and then we need to go and link to it and then call it. So include the library. The library is actually itself called log.age, but it's in Android /log.age. So this is how I'm going to include it as a system library. And now that I have it, I want to go and use it. But of course, how do I know what's available to me? Well, it just so happens that all these libraries, all these, I should say, header files are available as part of the NDK. So if I go inside of, in fact, I can just, let's say I vim it, inside of my developer Android NDK directory, I'll find here are my platforms, and then I'll have the different platforms that NDK is supported over the years, and so 14 is the latest one that I just happen to be using, and then I can pick, for example, one of the architectures. In this case, it's not architecture specific. Go to the includes directory, and then go into the Android log.age. That's the file that I'm actually importing, or I should say including, as a system header file. So what does this thing have? Well, it basically talks about, how you can do logging, but specifically down below, it defines a list of priorities that I could log at, and it defines essentially a print function, or I should say a log or write function and a log print function that I could use to log. So what I do is I would call this function, specify the priority, specify the tag, and then specify some sort of formatted string plus variable number of arguments that would be fed into that string. So let's go and use it. Here's the function I'm going to use. I'm going to copy this, go into my Eclipse, and so for example, say right here, I would go and say, okay, we're going to log. Now, how we're going to do the logging? Again, the first is the priority. Well, one of the priorities that is listed here is the debug priority. So let's go and log that. So debug. Then the next thing we need to do is specify the tag. Let's just, for the sake of argument, we're going to hard code it here. So I can say fiblib.c just for fun. And then I can specify the message. So this is that message, the formatted string. So I can say fib_nr of %d, right? And then I would say n. There's only one problem here. This %d, when it comes to printf, essentially assumes that the n you're feeding into this %d is an integer. Well, in our case, this is a long, so we would actually have to say an L in front of it. But because we're in a 32-bit platform, we need to say, well, this is not just a 32-bit long, this is actually a 64-bit long. So in order to get it printed correctly, you have to say LLD. Only then will it actually print correctly. In the Java world, this would not have mattered. We just say %d, for example, and that would get the job done. So let's do the same thing over here. So down below, I'm going to go right here before I actually go and step through this for loop. I'm going to say fib_ni and pretty much do the same take the same approach. So I am now done. Now the only problem is if I actually went to my Fibonacci native and did NDK build, it would actually not work because it would say, well, this is an undefined reference. It doesn't know where what this is going to link against. So in order to help the linker, I need to basically modify my makefile slightly. And what I'll do is inside of the makefile, I'll add an extra little bit, and that is I'm going to say local ld libs. Oops, I am looking at my keyboard and typing something completely different. Local _ ld libs equals, and now in fact I'm just going to plus equals in case there are any other ones, -l log. Hit save, And so now that I've done that, I can go back over here, rerun the NDK build, and now it essentially, the linker knows what to look for and what my code is going to bind against at runtime. And so now if I refresh and rerun, hopefully I'm going to get the logging working. So let's go and run it. Go back over here, type ADB logcat so we can actually see the logs from our code. And so go back to the emulator, put some number here, like, I don't know, 25 for JR, hit enter, and we get the fiblib JI 25. That's good. We can also do the NR. And so here's the fiblib.c. That's the tag we used, and it produces the, prints the correct number. So what this was an example of is essentially us, let's go back over here, using one of the, in this case, a simple header files, and then linking against the library that implements this header file, that basically Android guarantees will be supported in the future. So part of the NDK is essentially, let's go and take a look at this over here, is not only to give us, the basic tool chain, but also to provide libraries for things like libc, libm, the JNI headers for JNI itself, the compression library, liblog, which is what we've just used, support for OpenGL 1 and 2, support for lib JNI graphics, support for some minimal support for C++. This has actually gotten better over the releases, but initially it was really minimal. Support for OpenSL, and then of course support for building native applications or Android native APIs, I should say, which are still just a small subset of what the Java APIs support. Anyway, what's interesting is that Android, if you go to the developer NDK documentation, and you open this up, say, in a browser, you will see a whole bunch of obviously different things. But one of the cool things is you'll see this file called stableapis.html. This file basically tells you what are the stable native APIs, and specifies, the math library, C++ library, and so on and so on. And then specifically goes through this and says, okay, so if you want to use liblog, you want to be able to link to against this library, this is where you're going to need to add to your code, and it tells you which file you can take a look at to understand what are the capabilities. If you want to do zlib compression, take a look at this file, and then this is what you need to add to your make file. If you don't want to go and use other sorts of like OpenGL or OpenSL and so on, you'll basically go and look in this under the stable APIs HTML to understand how to appropriately include and link to this code. So that's it. We now see that this is possible and quite easy to do. So let's take a look at one more thing, and then we'll be wrapping up. So now that we have essentially a working application, the one thing I wanted us to explore is how we can potentially optimize it slightly. So one of the really good guides on the developer.android.com website talks about, among other things, designing for performance, and underneath specifically talks about some JNI tips. So one of the sections on the native libraries talks about this JNI onload function. And so what this will allow us to do is to, if we choose to implement our code in C++, allow us to execute, or I should say pre-register our functions with the Dalvik virtual machine as soon as our library is loaded, as opposed to waiting until the first time our code is used. Because what we don't know is, until our functions are first used, whether or not we have correctly mapped names from the function method names onto function names. Specifically, let me kind of explain. So here this fiblib function, or I should say class, has this method, for example, native static long fib_nr. And of course, this one over here has the same sort of method, call Maracana Android, blah, 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 fib_nr. The name of this function, it has to exactly match the name of this class, the package, and the name of this function. If it doesn't, it will not work. And the problem is, we'll only find out that it doesn't work the first time we try to use it. And at that point, it will be essentially, maybe too late. It's not something that we can preemptively test for. So what Android allows us to do is to actually pre-register these functions, essentially think of them as pre-bind them before they're actually even used the first time. So here's what I'm going to do. I'm going to make a copy of this C program, and I'm going to call this CPP, for example. So just create a C++ version of this. So here we go. And so now what I'll do inside of it, I'm going to close this original file, and I'm going to open this other file up. And now what I'm going to do is I'm actually going to, using in C++, I'm going to go and, first of all, I don't need this anymore, this header file. Instead, what I'll do is from this header file, I'll just take the jni.h, so that I do need, but this entire file can go away. In fact, I can say I don't need it anymore. And now I'm going to go, as opposed to using this long, naming convention that comes from Java, because C doesn't have namespaces. I'm now actually going to use C++ namespace support. So namespace, for example, com Maracana Android Fibonacci native. In fact, this it just happens to be something that I choose to do. It doesn't even have to match what I have in my Java classes. So let's just go and have this kind of nicely indented. This entire thing no longer has to be exported this way. So I'm actually going to get rid of this altogether. This is still going to return a JLong, but this doesn't have to be a JNI call. Instead, what I'm going to do is I'm just going to say this is a static function. So essentially, it's private. It's not exported anywhere. And in fact, this becomes redundant. I can actually call this whatever I want to. And I can even simplify it, make this look, slightly just in one line. Okay, so this I'm going to indent, this I'm going to indent, this I'm going to indent. Okay, so far so good. Same thing I'm going to do over here. This becomes a static, so static JLong also has, I also have to go and just fix something. I'm going to get rid of this. This becomes just an NI, just like we had before. I can go and move this up above, and I'm just going to go and indent all of this slightly. Nothing too exciting, really. Not changing the actual code, at least not how it behaves. And now I can go and close this namespace. So I'm just going to go down here and close the namespace. So now, of course, if I were just to compile it like this, how will the Dalvik ever be able to find these functions? Especially, A, they have names that don't match anything, and B, they are static, so they're not exported. So this is one last thing I'm going to do is I'm actually going to create a mapping. So specifically, I'm going to create a static array of JNI native method. So actually method. And this, I'm just going to call it a method underscore table, for example, like this. And this is going to essentially define a collection, or I should say an array of these JNI methods, each of which is going to essentially map a Java name, method name onto my function, my private function. It will act as a pointer to the function. So here we go. First, I'm going to go and define the name of the Java method. So for example, fib_nr. Okay, this is the name that was used right here, fib_nr. Then I'm going to say that this method maps onto a method, or sorry, I should say this method that I'm searching for by name. I also have to specify its type because Java supports method overloading, and so therefore I have to specify exactly which method I mean. Now, the way you express types is somewhat weird and it seems cryptic. But essentially what it means, I'm using the syntax that actually comes from JNI. It's defined right here. And if you see, for example, when you're defining signatures, if you see a J, that is referring to a long. If you see an F, referring to a float. If you see, a square bracket in front of something, that means referring to an array of that. If you see an L followed by a fully qualified class followed by a semicolon, that's referring to a fully qualified class. So essentially what I'm saying here is I'm looking for a Java method called fibnr that takes a J, again, J being a long, and returns a J. Okay? That's again just because of the Java support for overloading. I have to be explicit as to which method I'm actually referring to. And I'm now going to essentially make this be a pointer to the fibnr function that I've previously created, which is the one over here. I'm essentially pointing from a logical Java name to an actual function name. That's my first entry in this table. The next entry is going to be pretty much similar sort of thing, ni jj, because it also takes in a long, returns a long, and then this is going to point to this function right here, so I'm just going to say ni. That's it. I now have essentially a little table that describes how will Java methods map onto these static functions, essentially static functions through these function pointers. Okay, now here's the next thing I want to do. Now I want to register these. So I'm going to say using namespace. In fact, I'm just going to be lazy and copy the namespace down below. Okay, and now I'm going to say, okay, I'm going to build a static, an extern C function. So that returns a JInt. In fact, it could just return an int. That's called JNI on load. In fact, rather than type all of this, I'm going to be lazy and just copy this from here, like so. So copy and paste. I don't have to say extern. I like to. Simply, for consistency, it would work either way because it gets exported anyways. But what I'm doing here is I'm creating a special function that has a special name that will automatically be invoked by Dalvik virtual machine or any Java virtual machine for that matter when the environment is or when this library is first loaded. And so the whole purpose of what I'm doing here is so that I can actually connect my execute on this mapping on the load of my library rather than wait until the first use. Okay, so here's basically what I'm going to do. So now that I have the environment, okay, I'm going to go like this and say else. I need to go on grab my class. So how do I actually grab the class? JClass equals, or class equals environment env find class by a particular name. Well, what's the name of my class? Well, the name of my class is going to be, let's take a look. It's this one. Okay. Now, why am I looking for a class? The purpose here is so that I can go and point. So let's go down below. Go like this, and so that I can go and say, when you register these methods, unfortunately here they're all slashes, not dots. When you register, and then finally fib lib, when you register these functions, or I guess methods to functions, I need to tell the system as to what will register it on. Okay, so basically what I'm doing here is I'm looking for this class by this particular name. Okay, I'm going to assume that this class exists. Well, actually, I should not assume. I should just go and say, well, if class, if it doesn't exist, we're going to obviously have a problem. So if it exists, I'm going to go and register the native method. So I'm going to say env, register natives, okay, on this class from this table, right? So remember how I have this table that I built over here? So I'm going to have from this table, and I have to give it the size of the table. So the number of elements in the table, I can just say 2, or I can say size of this table divided by size of, the first element from this table, for example, right? Or I can just say the size of the JNI native methods. Anyway, what this will do, it will essentially tell the environment, the JNI environment, that we are going to look for these methods on this class and register those methods to point to essentially the following functions. So when these methods are requested to run, these functions execute instead. So the benefit of this is we do this once, we do it at the startup. If there's a problem, essentially we deal with that problem right away. We don't have to worry about that problem becoming a linkage error down below. So now that we've done this, we would want to go and get rid of our class. We don't really need the env a local reference to this class. So we say delete local ref and class, and so now we can say return 0. We're done. Otherwise, of course, so there was a problem, we're just going to say return, I don't know, -1 or something like that to indicate that we weren't able to actually complete this properly. This actually returns 0, I should say. We shouldn't return 0, we should just return the actual version. So I'm going to change this to say return the JNI version, and now we should be done. Okay, well, at least with this code. So ultimately, the benefit is all the registration and mapping happens sooner rather than later. So to test this out, I'm going to go to my make file. I'm going to change this to be CPP, right? Because I now have a new one. This file and this file, these two files are actually now being ignored. They're not used for anything. The CPP file is not at all looking at the header file. And so let's see if I did everything correctly. I should be able to essentially get my code to work. So let's try clean, and let's do an NDK build, and it compiles. So that's promising. Now I can go over here and refresh, and now I can go and rerun. Okay, so what we'll see is, again, we're going to go over here and type adb logcat. When our code first runs, at least when it first loads, it'll actually execute the on load, and it will be able to bind to everything earlier rather than later. So let's give this a shot. Like, for example, 15 on NR, hit this, it executes it. It doesn't. So it's telling you here that it's trying to load it, and right now it is loaded it, and actually it has already executed the on bind method, or I should say on load method. It has bound all of these. So let me go back to show it to you. So it has already executed this on load. It has already bound or found our class, registered all the natives, and then allowed us to actually run whatever function we actually ran. But ultimately, this is going to be slightly faster and slightly better in terms of being able to identify errors early rather than wait for them to happen later. And the reason why I wanted to show this is, while the JNI way, which is using the I should say Java age function to create a header file, which is what we got here, right? And then we also built this C file, right, to support it, and using this mapping, using the naming convention essentially. While that gets the job done, this is not how, for example, Android's own JNI layers do it. Pretty much all of Android is built this way instead, using C++ files that they not necessarily do much C++ per se. There's nothing object oriented here. It's still really pure, almost pure C code. But nevertheless, they're able to pre-register everything and detect errors and sort of run it slightly faster performance than if they did it using our initial approach. So just coming back to this diagram in this preview, you'll notice that if we do it this way, we essentially no longer need to do this anymore. And we are now building not a C but a C++ source file. The rest of it obviously remains the same. So just to summarize, I mean, what we did here is we just went over a very small subset of what NDK is capable of. But essentially, NDK enables JNI. JNI enables us to call into native code. Native code is there to help us, essentially take advantage of some legacy code we've already written or optimize parts of our application for performance. Android has a whole bunch of APIs, native APIs that we could take advantage of. So if you scroll over here, you'll see actually all those APIs. Or list of those APIs. We could try to use other sorts of system libraries, but these are not necessarily guaranteed to be stable and may change, so therefore our code may break. And ultimately, we should probably stick to these. We also saw that there are two ways of getting this done. One was to, build a native library, indicate native methods, compile it, extract the header file, implement the header file, create a make file, optionally create an application MK file, compile into a dynamic library using NDK build, then build a client app that actually uses this Java class, which then loads the dynamic library and completes the picture. In general, you should not use NDK just because you prefer to code in C and C++. It's not the most optimal way of building Android applications because of the increased complexity. Like, for example, your applications may become more brittle because memory management is no longer done automatically. And of course, they become less secure because of the also memory management. But ultimately, at least our applications are able to take advantage of code we might have already written, and we may be able to at least hand optimize code for increased performance. Anyway, I hope you enjoyed this. The code will be available online. I'll post a link to it, and good luck and enjoy coding in NDK.
Thanks for joining me. I hope you enjoyed the screencast and you learned something new about the Android Native Development Kit, and that you'll be able to take advantage of it in your future projects. I invite you to come to Murakana's stream for more educational tutorials, videos, screencasts on Android, but also on other open source technologies.